Yeah, so this is joint work with Tiago and Sam. So I guess I'll start by just briefly recapping the paradigm of error correction that we'll be talking about here. And it's just the standard setup. So we have a length k message phi, and we want to encode it into some length n message or some length n code word, so that if an adversary acts on delta fraction and corrupts delta fraction of the code word symbols, we can apply a decoder and recover some phi prime. And the typical goal is that for a given rate, the ratio of the message length to code word length, we want efficient algorithms for encoding and decoding so that the decoded message phi prime is equal to the original message phi for the maximum possible error weight, delta n. So again, that's our standard error correction goal. And there's known kind of fundamental limitations on how well we can do this. So the quantum singleton bound says that for a given encoding rate r, the maximum possible fraction of errors from which we can decode is 1 minus r over 2. And this bound turns out to be very robust. Intuitively, if you think of r as being something small, like approaching 0, then this bound is 1/2. And if you just think about it, you can never hope to correct from more than errors on more than half the code word symbols, because otherwise you could kind of just take a code state, split it into 2 parts, and then by applying the decoder to each part, you could kind of clone your original message. So we should expect this 1 minus r over 2 bound to be extremely robust. And yet if we move over to the setting of unknown error locations where we don't know where the errors occurred, it turns out that this bound actually drops by a factor of 2. We, in general, can only correct from errors acting on 1 minus r over 4 fraction of the code word symbols. So I guess what we're looking at in this talk is kind of, can we kind of replace this 4 with a 2? Are there some settings in which we can do error correction against unknown error locations, but still correct up to 1 minus r over 2 fraction of errors? And it turns out that we can do this if we relax from exact error correction to approximate error correction. So the only thing that changes here is now we only need to approximately recover the original message. And as you heard in the last talk, we can actually do this. This approximation doesn't have to be bad. It can be an exponentially small loss. So this approximation could be like exponentially close in like fidelity or trace distance or really whatever metric you want. It turns out that once we just introduce this small amount of approximation, a small amount of decoding loss, all of a sudden the fundamental upper bound goes back up to 1 minus r over 2 for the unknown errors location, for the unknown error setting. So now, at least in theory, for these upper bounds, there's no separation between known error locations and unknown error locations for approximate error correction. And in this work, we show that these upper bounds are basically tight. And I mean, that was already known. What we really give is we give an efficient construction of quantum codes that approach this bound down here. So we show that once you relax from exact error correction to approximate error correction, all of a sudden it doesn't matter whether the errors happen in known or unknown locations. There exist efficient encoding and decoding algorithms for quantum codes that correct up to the singleton bound in terms of the number of errors. So just to formally state our main result, we show that for every constant rate and for every constant loss parameter gamma, there exists an infinite family of quantum codes with rate r, constant alphabet size, assuming gamma is a constant, that correct arbitrary adversarial errors up to the singleton bound minus a gamma loss, and an exponentially small recovery error, which for all practical purposes is basically irrelevant. And formally, the formal statement of this approximate recovery is what you'd expect. Just the distance between the decoding of the corrupted state and the original message is exponentially small. And the key point here is that our construction in this theorem is efficient. So we give efficient encoding and decoding algorithms with these properties. So interestingly, our main result actually has no classical analog. So here I've stated the goal of classical error correction, and it should look very familiar. It's literally the same as quantum error correction, except in this box here, phi is a string of classical symbols. So just as there's a quantum singleton bound, there's also a classical singleton bound. And the classical singleton bound is double the quantum singleton bound. So for known error locations, classically we can correct up to 1 minus r fraction errors. And just like quantumly, for known error locations, the classical singleton bound is very robust. It literally follows by like a one-line pigeonhole principle argument. Meanwhile, with unknown error locations, just as in the quantum case, we again have a factor of 2 loss, in the sense that in general you can only correct from errors on 1 minus r over 2 fraction of the symbols classically, if you don't know the location of the errors. And whereas quantumly I just told you that we show how to close this gap efficiently, classically it's actually like information theoretically impossible to ever replace this 2 here with the 1 up here. So to close the difference between these two bounds. And the reason is kind of like a shifting of the goalpost between the quantum and classical settings. Essentially, because the classical singleton bound for low rates approaches 1, it means that if we wanna meet this bound for unknown error locations, we need to be able to correct from errors acting on almost all of the code word symbols. But it's actually in general impossible to do error correction, whether exact or approximate, on more than half the code word symbols, because if the adversary could corrupt, say, even just half the code word symbols, they could choose either the first or second half of the code word they receive and just in there like plant the encoding of a completely unrelated message. So the receiver would receive kind of the concatenation of 2 halves of code words of different messages, and they would have no idea which was the true message and which was the planted message from the adversary. So classically, we actually can never, like this unknown error location bound is also very robust. We can never hope to get rid of this factor of 2. And quantumly, somehow, because the goalposts are shifted, because this bound is already 1 minus r over 2, then we already have this factor of 2 loss, and so somehow quantumly, we don't have this impediment, which is, it's a little strange, but it really is just like a shifting of the goalposts. Oh, so I just told you why classically we can't approach the classical singleton bound. Now I'm going to tell you that actually we kind of can. We just need to further change our notion of decoding. So we can't do exact decoding up to the singleton bound classically. We can't do approximate decoding. What we can do is actually list decoding. So this is this notion. It's been very well studied classically. And the idea is we again start with a length k message. We encode into a length n code word. There's some corruptions that occur. But now instead of decoding to a unique message, we actually list decode. So the decoder outputs a list, maybe like a short polynomial sized list of possible messages, with the guarantee that the original message phi is in this list. So this list could be full of all sorts of junk, all sorts of completely unrelated messages, as long as it does contain the original message phi. And again, we want to do this list decoding for kind of the optimal trade-off between rate and distance. So it turns out that if we relax to list decoding, then classically we can get back to the singleton bound. So we can list decode from twice as many errors as we can unique decode, assuming errors in unknown locations. And just to put the numbers on that, as I mentioned, for ordinary unique decoding classically, we can correct up to 1 minus r over 2 fraction errors. For list decoding, we can get back up to 1 minus r. And furthermore, as I mentioned, list decoding has been very well studied classically, and there's efficient, explicit constructions known basically achieving all of these bounds. So this idea of list decoding actually suggests an approach to constructing approximate quantum codes. Here's a high-level outline. So we could first try to develop quantum list decodable codes correctable up to 1 minus r over 2 fraction errors. So if we had a notion of quantum list decoding, we could hope that like classical list decoding, it approaches or at least the quantum singleton bound, which would give this first bullet. And then we could try to somehow reduce the problem of doing approximate error correction to the problem of doing list decoding by somehow finding a way to filter out this list and just identify the true original message. Now this outline naturally has some challenges. The first obvious challenge is kind of how can quantum list decoding possibly be compatible with the no cloning theorem? The whole idea of list decoding is we're outputting a list of messages that are close to the true original message. And so this kind of inherently seems to say that we need to construct a lot of similar copies or nearby states to our original state, which seems to, like, by definition, contradict no cloning. Now, even if we could somehow get around this challenge and define quantum list decoding, we still need to be able to do it efficiently. And finally, if we have all of that, if we have some form of efficient quantum list decodable codes, then we still need to be able to reduce approximate error correction to list decoding. And I just explained to you why this is, I hopefully just convinced you that this is impossible classically, whereas we need to find a way to do it quantumly. So these are kind of the three main challenges that we need to overcome to kind of execute this outline and construct approximate quantum codes. And I'll now, at least at a high level, kind of give a one-by-one description of kind of how we get by each of these challenges. So the first challenge is how can we define quantum list decoding and make it compatible with the no cloning theorem? So classically, we typically think of list decoding as outputting a list of possible messages. That's the way I described it. It's the way that it's typically done classically, but it also, as I described, is not very compatible with no cloning. We can use an equivalent formulation where the list decoder instead outputs a single message along with a short list of possible errors, with the guarantee that kind of the true message is this outputted message, along with one of these errors in the list applied to the message. So it's kind of, instead of outputting all the messages, you output one of them and then the difference to all the other ones. And this approach actually does work quantumly. So this was, I think, first observed by Lung and Smith in 2008. In this work, we build on their work and further simplify their notion of list decoding. And the idea is that the list decoder outputs a single quantum message, phi prime, and then a short list of possible Pauli errors. And Pauli's, you can classically describe a Pauli error. So this is an entirely classical list. And that means that the decoder only outputs a single quantum message. So there's no issue with no cloning. And the guarantee is that the true message is this outputted message phi prime with one of the list elements applied to it. One of these possible Pauli errors has occurred. Now, there are some subtleties that arise here involving degeneracy. I won't get into that, but this is the main idea. Okay, so now we want to find a way to construct efficient encoding and decoding algorithms that do list decoding up to the optimal singleton bound. And as I mentioned, classically, this problem has been solved, and it was originally solved in 2008 by Guruswamy and Rudra, where they came up with these things called folded Reed-Solomon codes, which I won't have time to get into, but it's a beautiful construction that achieves this almost optimal classical list decoding. And as I'm sure many of you are aware, quantumly you can construct a quantum code from two classical codes. This is just what CSS codes do. And we can observe that if the two classical codes in a CSS code, like the X and Z codes, are efficiently list decodable, then so is the quantum code that they form. This is almost by definition if you just trace through all of the definitions here. And so it turns out that these folded Reed-Solomon codes, they satisfy all the orthogonality conditions you need for CSS, and you can make them work in a CSS construction. There are a number of complications. You have to be careful how you define things, especially with this folding. You need to do some work to ensure small alphabet size, which I'll talk about more later. But at a very high level, we really just are using this classical code and just sticking it directly in a CSS construction. And out of this, we get efficient quantum list decodable codes up to the quantum singleton bound. Oh, so the final challenge was kind of going from quantum list decoding to approximate quantum error correction. And the challenge here is we assume that our list decoder has given us a list of errors. So a short like polynomial sized list, E1 through EL, of classically described Pauli errors, and we want to identify which of these errors has actually occurred. So an initial observation here is that the list decoder, what it's really done is it's reduced the problem of correcting from an arbitrary low weight error to the problem of just correcting from this very short list of errors. So the list decoder has drastically reduced the set of possible errors. And now that we have such a short list, we can actually just use like a very high rate random stabilizer code. And like a very high rate random stabilizer code will still be able to cope with a polynomial number of errors with high probability. So if we pre-encode our message in a high rate random stabilizer code, then with very high probability, this random stabilizer code will be able to detect all the extraneous errors. It will be able to cope with all of the incorrect errors in this list, and we could identify the true error. Now this is great, except for the fact that the randomness needed, the amount of randomness we need to sample this stabilizer code is relatively high. It's high enough that we actually run into some trouble if we try to use this, because the decoder needs to know what this choice of random stabilizer code is. And we can't set it initially because the randomness needs to be independent of the errors. So the adversary can't know these random bits. So if we just do this approach, it works really well, except we would kind of need like a giant side channel to communicate like all of these random bits to the decoder. And we get around this challenge by essentially replacing the random stabilizer code with a pseudo-random stabilizer code. So again, this is an idea that was, I think, it was used by Lung and Smith in 2008. We, again, build on their work. And actually, a follow-up by one of my co-authors, Tiago, further builds on our work. But the high-level approach is to use the pseudo-random stabilizer codes, something called the purity testing code. And essentially, it turns out that this suffices in place of the random code. We then need to convey the choice of pseudo-random code to the decoder, but now there's only like a few random bits, so it turns out we can use like a classical robust secret sharing scheme. It's some primitive that was already known, and that can essentially communicate our classical secret key. So this is our main result. I'm just flashing it up again. We get efficient approximate quantum codes approaching the singleton bound. And I've described all the main ingredients, so I'll just briefly outline how we put them together. So we start with the message fee. We encode in a PTC. So this is the pseudo-random stabilizer code for a random choice of this secret key kappa. We then encode in the quantum list decodable code, the quantum folded Reed-Solomon code that I mentioned. And finally, we encode the secret key in a classical robust secret sharing scheme. And then we append the secret shares to the symbols of the list decodable code. So each symbol of our final code is just a symbol of the list decodable code concatenated with a robust secret share. The point is now, if we want to decode, after some adversary has done some corruptions, we can separate out the secret shares from the list decodable part, apply the RSS decoder to recover the secret key kappa, apply the list decoder to recover a message with a list of possible Pauli errors, and then use the secret key kappa in our decoder to essentially use the PTC, the pseudo-random stabilizer code, to try to detect all of these errors. And if we detect any one of these Paulis has occurred, we know that's the true Pauli, and so we can just invert it and recover our original message. Now, it is worth noting that this last step here is where all the approximation comes in. Everything else was exact, but because this PTC is like a pseudo-random code, there is a small chance that we choose a bad secret key that can't actually detect the true error. So this step here is where the approximation comes in. So yeah, that's a very brief overview of our construction. I did just want to highlight one of our techniques briefly. So as I mentioned, we need to do some work to reduce, or I guess to reduce the alphabet size down to a constant. And we actually use this distance amplification and alphabet reduction technique of Alone, Edmonds, and Luby. It's been long used classically, but I think to the best of our knowledge, we're the first ones to do it quantumly. And since our work, there's actually been multiple additional uses in the quantum literature. But at a high level, basically the idea is just to take a message, encode it in an outer code, and then concatenate that with an inner encoding, and scramble the symbols with like a permutation given by an expander graph. And the point is this permutation, when you do decoding, it scrambles the errors so that they're not concentrated within any inner code block. And I don't think I have time to go into more depth, but at a very high level, it's just this kind of simple concatenation followed by a permutation scheme. Yet it seems to be very powerful. And so, for instance, just applying this to asymptotically good quantum LDPC codes, we automatically get quantum LDPC codes approaching the quantum singleton bound. So it's just something you can get for free by just pasting in the AEL technique. So just to wrap up, as I mentioned, there's been some follow-up works to our work. Again, using AEL amplification for locally testable codes and quantum locally recoverable codes. Tiago, one of our co-authors, also has a very nice follow-up work on keyless authentication. So essentially removing the need for this purity testing code. This allows for applications to the case of binary alphabets and further applications to qubit-wise channels like beyond even approximate quantum error correction. So that's a very interesting work. I suggest you check it out. And I guess just conclude with some open questions. So can we go further down the route of binary alphabets? Can we extend list decoding to non-stabilizer codes? Everything I talked about was just for stabilizer codes. And can we get more applications of our techniques? So thank you.
Thanks very much. Do we have any questions? Yes, please use the microphone in the middle.
Thanks for the good talk. I want to ask why you need to use this PTC code. Like, you mentioned that you need to randomly sample this to be a high rate code. The immediate question is, why don't you just pick like a well-chosen code? Why do you have to do this random step?
Right. So the key point is we want to be able to, the Pauli errors, the list like E1 through EL that the list decoder gives, these are dependent on the choice of I guess the adversary can implicitly choose their corruption, which determines this list. And so for any given fixed code, if we replace the PTC with a single code, there would be some error that, like, these are not necessarily low weight errors. These could be high weight errors.
I see.
We only know there's a small number of them. So
okay.
for any fixed code, the adversary could find a corruption that beats that code.
I see.
But since the list is short, we know that a random stabilizer code will with high probability. So it's like this kind of, we choose the code after the adversary instead of before.
Yep, got it. Thank you.
Next question.
Hi, thanks for the great talk. So classically, there's this relationship between list decodable codes, expanders, and randomness extractors being like incarnations of the same object. Does this sort of definition of yours also have the same relationship between different, I guess, quantum combinatorial objects?
Yeah, I think that's a really interesting question. I don't know. I think we looked into this at one point, trying to see if there's some connection between like quantum pseudorandom things and quantum list decodable codes. And I think we weren't, at least I don't think we were able to find any connections at the time, but I think it would be a little surprising if there weren't, given how strong the connection is classically. So I think it's a really interesting direction.
Hello, thank you for your presentation. Actually, I had two questions. The first one is, what do you mean exactly by known errors and unknown errors? Is it the same as errors coming from loss and body errors?
So yeah, I think what we mean is so by known errors, I mean the locations of the errors. So it's like erasures. Whereas for unknown, it's like you don't know the location of the errors. So an adversary can choose to corrupt certain symbols. You don't know which ones are corrupted.
Okay. And then my second question is, what is the connection between these upper bounds and the one coming from channel capacities? Because I initially thought the motivation for approximate error correcting codes was to have codes that approach the channel capacity. But you never mentioned this in your talk.
Oh, yes, this is a good point. So I think we consider constant size alphabets, but like large constant alphabets. So like for any, we'll typically consider like a relatively large alphabet. And I think as the alphabet size grows large, I think all bounds approach the singleton bound. In the sense that like you can achieve the singleton bound and you very much can't go beyond the singleton bound. For
alphabet, you mean the
like
local
the local
alphabet?
dimension.
Okay, so in the limit of a local dimension going to something large, you say the channel capacity goes to the singleton bound.
Oh, I'm not sure which. I'd have to double check on what you mean by Shannon capacity.
Okay, we
But
can discuss it after.
oh yeah,
Thank you.
thanks.
Okay, are there any more questions? Yes, one more.
Forgive me if this is a dumb experimentalist question, but this talk seems to mostly be about communication using encodings. Does this sort of technique also work for encoded computation, or is the scrambling and the little appendages make it harder?
I'm not sure. We haven't thought about that, but that's an interesting question.
And yeah, maybe one final question.
Yeah, so thank you for the talk. I'm asking about the time complexity of the decoder. What's the most time consuming part of this decoder, or you are adding some secret keys? Is this time consuming, or is it as a whole? Is it polynomial time decodable, or could you clarify a little bit about?
Yeah, so the construction I stated is polynomial time, but it's a pretty bad polynomial
Okay, yeah.
because folded Reed-Solomon codes have a really large polynomial, like the exponent's really large.
Which part is dominant?
The folded Reed-Solomon decoding. We actually can. So in our paper we have another construction that I didn't mention here that kind of shortcuts out some of the folded Reed-Solomon part. It kind of does like AEL amplification directly on a small approximate code, and there you can actually get a better runtime. I guess there's also the RSS part, which I forget exactly the runtime, so it's a little complicated. I don't remember everything, but for at least certain parts of the construction, I think you can get as good as linear.
Mm-hmm.
But
yeah, thank you for answering.